Hi class, I wanted to review some basic terminology and notation with regard to periodic functions. This is background to our discussion of Fourier series. So we're going to consider a periodic function as a function that can have a graph of the following form. If we plot it with respect to time, say t, there's a fundamental domain, a fundamental period from, say, minus capital T over 2 to capital T over 2, so a distance of capital T. So the value of the function repeats every t units. So f of x plus t is f of t. So capital T is the period. I've used capital T thinking of the period in terms of time. It is also possible to consider periodic functions in space. In that case, we usually talk about the wavelength of the function, and we would plot it from minus lambda over 2 to lambda over 2. Now, this is an arbitrary choice. We could have chosen, instead of plotting it from minus t over 2 to capital T over to plus t over 2, we could have chosen to plot it from 0 to capital T. But I'm using the notation and the convention that we're going to use in this class. So there are some basic harmonic functions that we are going to be using constantly. These are simple harmonic functions. So the simplest example is, say, is a function y of x and t, which can be written as a cosine of kx minus omega t. So this might represent the oscillation, say, of a string where the vertical displacement is y, and x represents the horizontal position of the string, and t represents the time at which you're talking about the motion of the string. Then on the right-hand side, this simple sinusoidal function, capital A is the amplitude, how high the wave is. And this kx minus omega t tells us how the motion of this string with amplitude a moves along the string in space and time. So if you think of t fixed, it's periodic in space x. If we think as x fixed, it's periodic in time t. In fact, this combination corresponds to a right-moving wave. If we talk about a constant phase, where, say, kx minus omega t is some constant, then the crest, the phase of constant, the position of constant phase, as t goes forward, x moves to the right. So this is a right-moving wave. If we had kx plus omega t, which is also a simple harmonic wave, that would represent a left-moving wave. This kx minus omega t can equally well be written as the combination 2 pi over lambda times the quantity x minus vt. So let's take a minute to think about that. 2 pi is the fundamental period of a cosine of a simple sinusoidal function, and this 2 pi over lambda scales position x into wavelength lambda. And the combination, if we remember, if this is the right-moving wave, a fixed phase moves to the right with velocity v. So this combination, kx minus omega t, can equally well be written as 2 pi over lambda times the whole quantity x minus vt. Equating these two expressions, we see k, which is known as the wave number, is just 2 pi over lambda, this prefactor here. V is the phase velocity, and in fact v is just omega over k, because if I factor out k, I get omega over k. If we instead think of what the omega is, what the time dependence is, well, the cosine has frequency, has a period 2 pi, and we want the period to be capital T. So this just scales, omega scales from period in time, capital T, to 2 pi. So omega is 2 pi over capital T. This is sometimes written as 2 pi nu, where nu is the frequency, 1 over t, and omega is known as the angular frequency. So this is the basic harmonic function that we're going to be using over and over again. Now, in addition to the fact that we can consider right-moving and left-moving waves, we can also imagine a phase shift of this cosine, which, using the addition formula for cosines, I can write as some combination of cosines and sines. So I could equally well think about a cosine and a sine as my basis, or I could imagine displacing the phase by the phase of the argument of the cosine by some arbitrary amount phi. Finally, connecting to Euler's formula, we can also think of this a cosine kx minus omega t plus phi as the real part of this complex exponential function. And so often when we do calculations, it will be more convenient to think of it in terms of these complex exponentials. The convention that we're going to use in our class is we're going to be largely concerned, or we're going to use a notation that's most appropriate for functions that are periodic in position space, and we're going to consider the basic interval of the basic period to stretch from minus L to plus L. So the period or wavelength of the harmonic of the oscillating function, the periodic function we're talking about, is actually going to be 2L in our notation. The reason for choosing this fundamental domain symmetric around the origin is that allows us to classify the oscillations or the functions, the periodic functions we're talking about, into odd and even functions. Even functions are those that are even around reflection in the origin, which mathematically means f of minus x is plus f of x. So cosine x represents an even function, is an example of an even function. An odd function is of the form f of minus x is minus f of x, so sine of x is a fundamental odd function. What we will see ultimately is that often we'll be interested either in functions that are only even or odd, and we're going to be expanding those in terms of basic periodic functions, cosines and sines. If we have even functions, they'll only involve cosines, and if we have an odd function, it'll be an expansion only involving sines. In general, if you have an arbitrary function that's neither even or odd, we'll need both cosine terms and sine terms. Finally, the last set of things that we need for background of our discussion of Fourier series is to start talking about some integrals of periodic functions, or integrals of functions themselves. First of all, just reminding you the basic definition of the average value of a function from calculus is the integral over the region you're interested in divided by the length of the region. Since we're interested in the region from minus L to L, and f of x is a periodic function, we can define the average value of that periodic function to be 1 over 2L times the integral from minus L to L of f of x. The basic trigonometric integrals that we're going to need are the following. The average value of the cosine function from minus L to L is either 1 if m is 0, because after all, if m is 0, this is just a constant function 1, so its average value is 1. Or if you have a non-zero m, if you're talking about something with non-zero oscillation inside the period from minus L to L, it averages out to 0. That makes sense. If you think about the plot of the cosine, it spends as much time above the axis as below the axis. The average value is 0. Similarly, the average value of the sine function is 0 as well. The last two sets of integrals that we're going to talk about that are going to be useful for us for Fourier series are average values of products of sines and cosines. So if we look at the average value of cosine mx times cosine m pi x over L times cosine n pi x over L, let me emphasize that this combination m pi x over L is a cosine that has m full periods within the region from minus L to L. That's what this m pi means, m being an integer. Then the interesting thing is, if m is not equal to n, the integral of this product of cosines is 0. Similarly, for m not equal to n for products of sines, the integral is 0. And the integral of a product of a cosine and a sine is 0. This should be familiar. This is a little bit like what happens in basis vectors. Like if we think of the basis vectors I, j, and k in Cartesian coordinates, I dot j and j dot k and k dot I are all 0. In fact, what we're going to see is these cosines and sines, cosine m pi x over L and sine of m pi x over L, are like basis vectors for all periodic functions from the interval from minus L to L. And these relations tell us that these basis functions are actually orthogonal to one another. The last thing we need to do is in that mode is to actually compute, if you want, the magnitude of the basis vector itself. That's the integral from minus L to L of cosine squared of m pi x over L divided by 2L. If m is 0, again, this is 1, so you get the average value is equal to 1. But if m is not equal to 0, you find the result that you're probably familiar with, that the average value of the cosine squared is half. No matter how many periods, full periods of the cosine you have inside the interval. And similarly, the average value of the sine squared of inside an interval is equal to 1/2 as long as this n is not equal to 0. So this is the basic relation that you should remember. The average value of the sine squared of the cosine squared is 1/2. What we're going to see in the following lectures is that we can take these cosines and sines and treat them as basis vectors for the periodic functions on the interval from minus L to L. And that will allow us to expand, just like we can take a vector and expand it in terms of basis vectors, we can take an arbitrary periodic function and expand it in terms of these fundamental periodic functions, sines and cosines. And in fact, that expansion is precisely what we mean by the Fourier series.